Okay, so today we're going to be looking at 1.14, function model construction and application. So in this lesson and moving forward, there will be many times that we'll be given data like we see in problem 2, that data down there, and we'll be asked to find models that fit that data well. And we'll be asked to do things called regressions. Finding different models that fit the data. Okay. So we have the different type of models that we're going to be looking at. What we've seen so far this year has been polynomial and rational functions. Later on, we'll also be looking at exponential models, logarithmic models, sine, cosine models. We're going to be doing regression models for all these different types of functions. But for right now, we're going to be focusing on our polynomial models. Now, before we get into that regression piece, we have a little bit of information that we have here, and that is going to be that we want to find a polynomial model of degree n, and if we have that, we'll need at least n plus 1 points. What's up, guys? Gabriel is not here today. Sorry, guys. So again, if we have a polynomial of degree n, how many points do we need? What does it say here? N plus 1. What does that mean? Well, let's go into this example to see what that means. So if I want to find a linear model, what is the degree of a linear model? What is linear? What's the equation, like a general form of equation? Y equals mx plus b. What is the degree of y equals mx plus b? 1. So then if I have degree 1, how many points will we need? 2. Why 2? The degree plus 1. So 1 plus 1 is 2. We would need 2 points, which makes sense. Let's think about that. If I have 2 distinct points, can I create a line through that? Yeah, I can. I can say, hey, there's a linear equation through those 2 points. We've done that before in previous classes where we said, hey, here's 2 points, finding the equation of a line through the 2 points. That's what we're doing. We're finding a linear model given 2 points. So then if I have a cubic, how many points would I need? What is the degree of a cubic? 3, so how many points would I need? 4 points. It is the degree plus how many? It's just 1 more than the degree. That's all it is. So if we have cubic degree 3, say third degree, then we would need 4 points. Okay, so it's always 1 more than the degree. So what if I wanted a degree 9? How many points would I need? 10. I need 10 points, 1 more than the degree. All right, let's go ahead and move down to problem number 2. Problem number 2 says let d of t represent the average difference in life expectancy between females and males, so female minus male. So their average life expectancy. T years after 1940. Answer the following questions using the data and graph below. So we have all these data points from 0 to 70. This is actually not all the data points. If you actually go, this is real data gotten from, what does it say there? The Humane Mortality Database. That's interesting. Humane Mortality Database. This is from their database. And so in the actual data, there was a lot more data points. I narrowed it down to these, which is still a lot of data points, but it was able to narrow it down. So why is a quadratic model a reasonable model for D? What is a quadratic model? So let's go back to that 113, previous page, previous notes. What are some of the characteristics of a quadratic? What's the first one? Symmetry and data values. So that means that there should be some place where data values kind of start repeating. There's some symmetry going on. What's our next one? Constant second difference. So that's our second difference is the same. That works better if I'm given like small collection of data. We can look at the second difference. What's the third one say? Distinct min or max value. Why? What's the shape of a quadratic? A parabola, right? Parabolic. It has that parabolic shape. Does a parabola have a distinct min or max? Yeah, it does. It has that absolute distinct min or max. The next one is a geometric context. We're not dealing with a geometric context. We're dealing with something else. So let's go ahead and look back at the data. First off, looking at this graph, does this have a parabolic shape? Yeah, it does, right? We can kind of see, hey, that's kind of a parabolic shape, isn't it? For most of the data. When does it stop being parabolic in nature? What about right here, right? What year is that? Looks like around 2000, right? So up until 2000, this data follows more or less a parabolic shape. So for most of the data, is a quadratic a good choice? Does it follow kind of that parabolic shape? Yeah. So that would be one of the reasons. Why is a quadratic model a reasonable model? Well, we can say it definitely has that parabolic shape. Let's see. One of the other things we said was a distinct min or max. Does this have a distinct min or max? What does it have? Is it a min or a max here? Definitely have that max value up there. So I would say there is definitely a distinct max for sure. And is there somewhat of symmetry in our data? To see that, what if I draw a dotted line down at that max? Do we kind of have symmetry on either side of that dotted line? If I was to fold these parts on top, would they kind of lie on top of each other? Yes. Up until 2000, right? At 2000, that symmetry stops happening. But up until 2000, we kind of have that symmetry kind of happening. We can kind of see it in our data as well. If we kind of look at our data and say maybe 35 is that kind of place where the symmetry, the middle there, that's our max value. And I look on either side. They're not exact, but is 6.08 and 6.01, are those close to being the same? I go to the next ones, 5.58, 5.72. Are those close to being the same? And it's not going to be perfect, but is there maybe what we can call rough symmetry? Yes. So we can go ahead and say, hey, yeah, there is rough symmetry happening. Okay? It's not perfect, it's not exact, but there is definitely rough symmetry happening. Now it says, let's look back at this right here. It said a good reasonable model for 0 to 60. What is that in the years? Let's go back and see. What does it say our t is? Let's underline this. T years from what? After 1940. So what would 0 be? 1940. What would 60 be? 2000. Does that make sense? 60 years after 1940? Yeah, that's 2000. And again, what did we say our data is good until? 2000, right? So they're acknowledging that fact as well, that it's a reasonable model from 1940 to 2000. After 2000, it starts leveling out. It's not really a good model anymore. Okay? All right, part B. It says, let d of t equal at squared plus bt plus c for some values of a, b, and c. What is the minimum number of data points you need to determine the values of a, b, and c? What's our degree? How many data points do we need? 3, right? Because it's the degree plus 1. So that's an easy question. We need 3 data points. Minimum. Can I have more than 3? Yeah, we have a lot more than 3 up there. But we need minimum of 3 to build a quadratic. I can't build a quadratic from 2 points. But if I have at least 3, I can build a quadratic. So, in part C, we see they picked 3 points. There's the 3 points right here. And using a system of equations, which is a long process, so we're not going to do it, they found this data model right here. Is this model a quadratic? Yes. Does it have a degree 2? A, B, and C are big decimals, but it's still just a quadratic. So it says use this model to predict the average difference in life expectancy in 1983. Well, first off, it says average difference. Average difference. What is average difference? Let's go back up to the top. What does it say d of t represents? There it is. So what is average difference? D of t. So they're saying use this model to predict the d of t in life, so the average difference in life expectancy in 1983. To find d of t, 1983, I need to know what t is. What if I have 1983, what is my t? What was our t in? What was it? Number of years after what? So how many years does it take us to get to 1983? Makes sense, right? 1983 minus 1940, 43 years. So my t is going to be 43. It's 43 years. So this question, when they ask us to use this model to predict, all they're asking us to do is find d of 43. What is d of 43? So using this, I do that. How would I find d of 43? What do I do with 43? Plug it in. Do I have an equation for d of t? Yeah, so plug it in. Definitely not doing that by hand. So use your calculator. Plug it in. Find out what d of 43 is. That's our prediction. All right, how's that going, guys? Do we have it plugged in? Did we get this? 6.082488. Good job. Okay? Again, I didn't put it into Y1. I just plugged it in like this. Plug it in. Okay? If you put it into Y1, that's not a bad thing. It works, right? But remember, using the Y1 and then doing the Y1 of 43 is a great skill, but it's more useful if I have multiple things I'm going to be plugging in. If I'm just going to plug one thing in, just do this. All right, So 6.082, we can round to 3 decimal places. So that is 6.082. All right, according to research, the average difference in life expectancy between females and males in 1983 was 5.84. That's the actual amount. The actual difference. Was our prediction close to the actual amount? So our prediction was 6.082. Actual 5.840. Is that close? Yes. This is all based on the data from that website that I mentioned. Okay? So, they're asking how close or far off was your model's prediction from reality? What would we do with those two numbers to determine how close or far off we are? Subtract. I would take, which one am I going to subtract? What are we going to do? So what's my subtraction problem? 6.082 minus what? Okay, what does that equal, guys? 242. This is what we call the error in our data. So when they talk about errors or margins of errors, it's a statistics term. A margin of error, it's the difference between your predicted outcome and the actual outcome. So when you do our predicted minus actual, that is called the error in your data, your margin of error. Okay? Yeah. It tells you how far off you are, how good of a prediction your model makes. Okay? So what we're doing here with finding these models, and I'll show you how to find a model with your calculator in just a moment, is this is stuff businesses, hospitals, all these things do all the time. Is they have statisticians working on data all the time to make predictions. So they have all this data and they say, hey, we want to know what our profit will be next year. They don't have actual data, but they might have years worth of data. They use that to make predictions. They say, what model best fits this data? Let's find an equation for it. Let's use that equation to maybe predict where we will be next year. So they use this to predict outcomes. The error is how good of a prediction does your model make? And so we can use that to say, hey, our margin of error is only 0.2. It's pretty close, pretty good. If it was like margin error of 10.0, that's pretty far off. Not a very good prediction. Okay? Does that make more sense? So that's what we're doing here. We're doing stuff statisticians do. Okay? All right. Do you think your model will overestimate or underestimate the actual difference in expectancy in 2010? To see that, let's go back up to our data. So the green one is our prediction. The green one is our prediction down here. Up here in black, that's the actual. Here is 2010. 2010's about right here. If we go up, is our prediction an overestimate or underestimate of the actual amount? Is our prediction an overestimate or underestimate than the actual amount? It's under, right? It's less. So that would be an underestimate. So we'd say here, it is an underestimate. Now, they asked us to explain. So, an explanation that we could say is that the data starts leveling off after 2000. We saw that. We see that in our data. After 2000, our quadratic is no longer a very good model. So the data starts leveling off, but our quadratic model keeps decreasing. So if we think about something kind of leveling off versus something that keeps decreasing, eventually the decreasing will definitely be lower than the stuff that was leveling off. And so it will definitely be that underestimate. All right, once you have that, go ahead and turn the page and get your calculators ready. All right, we are using the same data. We're using the same data. We are now going to use our graphing calculators to find a regression, a quadratic regression. So in the previous page, we were given a quadratic model. Now we're going to use technology to find a quadratic regression model. Okay? So to do that, we are going to need to enter all this data into our equation, or into our calculators. I'm going to do the TI calculators first. Those with Casios, just hold a second, I'll get to you in a second. TIs I'll be doing first. Alright, so on the TI calculator, you are going to click the Stat button. Do we see the Stat button? S-T-A-T. Kind of circling it. I don't know if you can see my little icon. It's next to the arrows. Do we see the Stat button? So do you see the alpha green button? Go over to. There's your Stat. It's now highlighted red. Click Stat if you didn't already do so. In here you have some options. You have Edit, you have Calculate, and you have Tests. We are going to go to Edit first. The first option says Edit ... Go ahead and select that. So I'm selecting Edit. You should now have these lists shown up. Do we see lists, guys? If you have any data in there, say I have some data, you're going to go highlight your data and you click Delete. You just delete all the data in there until it's blank. If you do not see L1, L2, L3, L4, please let me know. Please do not go up and select L1 and press delete. It will delete the entire list and make it not be there anymore. Do not do that. If you did that, let me know in a second. I want to get you started entering data. Okay, so just hold a second, please. All right, you are going to now start entering the data in our notes. All right, what is our first t value? What's the first t value, our first input? So you're going to, under list 1, you're going to put all the input values. So we have 0. What's next after 0? 5. What's next? What's next? And you're going to enter in all of your t values in list 1. What do you think we're going to put in list 2? The d of t values. What's my first d of t value? 2.96. What's our next d of t value? 3.48. What's our next one? 4.13. What's our next one? 4.6, and so forth. TI calculators, people, Enter in your data, please, in list 1, list 2. All right, I'm going to go ahead and show you how you can also enter in your data on a Casio calculator, and then we will find our regression models for on both TI and the Casio calculators. So on the Casio calculators, we're going to go ahead and turn it on. We want to go to Menu, and in Menu, I'm going to go ahead and pick my Stat option, just like the TI. It's going into the stats. We're going to be doing the stats here. So go ahead and enter into stats. I need to go ahead and exit out all of that. So this is what you should see when you first get into your stats. When you click on stats, a place to enter in for list 1 and list 2. Now, as you can see, I've already entered in all the data, but you're going to go ahead and enter in the data just like I explained for the TI calculators, where we have all our input values under list 1 and all our output values under list 2. So for our example would be all the t values and then all the d of t values under list 2. So go ahead and enter all those in if you have a Casio calculator. All right, now I'm going to go ahead and kind of side by side talk about how we can find our regression equations on each of these calculators. So on both the TI and the Casio, we should have our information entered. So it's TI, I'm going to go to Stat and then Edit again. And so as you can see, I have all my data entered here on the TI as well as the Casio. So on the TI, so on both of these, let's go back to our notes real quick. On both of these, we're wanting to find that quadratic regression. Quadratic has that degree 3, so we're going to be like ax squared plus bx plus c. That would be our quadratic regression. So we're going to go ahead and enter or figure out what that regression would be using our calculators. In the previous problem, we were given a quadratic model that we used right here, but now we want to see what the calculator gives us and maybe how does it compare to the one that was given us on the previous page. So back to our calculators. On the TI, I'm going to go ahead and do that one first. On the TI, we're going to go back to our stat menu. So we're going to click on Stat. And then we're going to go over to Calc, because we're going to be calculating regression. So just press the arrow over. So over arrow. And then we see all these different regressions. The one we want is going to be number 5, the quadratic regression. Go ahead and go down and select quadratic regression. Now on the TI, there's a little bit more that we have to do. List, the X list, Y list, you can leave those alone. Frequency list, all that, we go ahead and leave alone. I want to go down to store regression equation. There, you're going to go ahead and say, I want this to be stored in one of our Y vars. You know how under Y equals we have Y1, Y2, Y3. We're going to store it into one of those. And this one, I'm just going to store it into Y1. So I'm going to go ahead and go alpha trace for my shortcut to get Y1. And there I'm storing it in Y1. On our older calculators, we would go to vars, Y vars, function, and then select Y1. Once you have selected Y1 for the storing the equation, I'm going to go ahead and hit calculate, and it calculates my regression for me, my A, my B, my C. Now there's also this R squared. We'll talk about what that means later in the course. Right now, if you have it, you can ignore it. If you don't have it, you don't need to worry about it. All we need is the A, the B, and the C for our regression equation. When you write it down, you want to give 3 decimal places. When you write it into like a test quiz, your homework, give me 3 decimal places. But because we stored it, if we go now to Y equals, we now see that it has been stored into our y equals, and I can now use it. We'll do that in a second. Going over to the Casios, this one's in some ways is easier, but really it's just different. We've entered in our data, and I'm going to go, actually, I'm going to go back because I want to compare these. It's number 5. Already stored it, so I'm just going to calculate. All right, so on this one, we also need to calculate, but we see calculate right here. So that's going to be our F2. So go ahead and select F2. We want to calculate a regression, so I'm going to go ahead and say, hey, F3. And we're doing a quadratic, and as we remember, quadratic is has the highest power of x squared. So I'm going to go ahead and pick x squared. Let's go ahead and pick x squared, and there's my regression. I don't have to worry about all that list 1, list 2, any of that stuff. So it's all there. And if we compare these are the same values. The only difference is the Casio is writing my a value in scientific notation. So the e is our times 10 to the negative 3. So we just move my decimal place over 3 spaces, and I get 0.002. And we can say it's the same values that we see here. Now, we stored our regression equation on the TI. We can do the same thing in the Casio by going over to copy. So that's F6. So F6. And then we just select which one we want to put it into. I've already stored it before, but even if you have something here, you can go ahead and just select. You just highlight which one you want to put it under. I'm going to put it under, well, I'm just going to put it under Y1. So do that, and then you hit enter, and it has been stored. We can double check, just like we did on the TI. Went over here and saw, hey, it's in there. I can do the same thing. Exit out of that, go to menu, and maybe go over to either graph or table where I can see my y equals, and there's my equation. Okay, so we have our equation inputted, which is what we want. And now let's go ahead and go back to our notes and write down what our regression was. So for this one, we can go ahead and say our regression d of t is equal to, that was equal to negative 0.002 t squared plus 0.168 t plus 2.792. Again, we round or truncate to 3 decimal places, and that is our regression equation. Next part, part B, we want to go ahead and graph the scatter plot of the data and each of the quadratic models that we have found. How does the model given in problem 2 compare to the model from the calculator? So problem 2, that was back here. So we're going to go ahead and graph this one as well as our data and the equation that we have. So let's go ahead and do that. Start by entering into that equation. I'm going to put under y2. So going back to my calculators. So under y2, so going to y2, I'm going to go ahead and I'm going to enter that equation in y2. All right, so I have my equation. So y1, again, is my regression that I found using the calculator. Y2 is the equation that gave me back in problem 2. And we're going to go ahead and compare these. Now, it does ask me, looking at the notes, it asks us to, let's see, graph the scatter plot. So we're going to go ahead and talk about how we graph the scatter plot of the data and each of the regression models. So we're going to go ahead and do that. So back to our calculators. So on the TI, there's a little bit more involved. We're going to go to stat plot, which is here in blue. I'm pointing at it. Okay, in blue above the y equals. And so we have to go second y equals, second y equals. And here are all my plots. I'm going to go ahead and enter into number 1. So just select it, enter. And we're going to go ahead and turn it on. I'm going to go ahead and use just the dots there. Now here I want L1 and L2 because that's where I entered in my data, so we're good there. Marks you can go ahead and leave with the little square. If you want to put dots, it's up to you. I'm going to leave it with the little square. Then you can choose a color if you want. All right, doing that is going to plot all my data as well as my equations that I have. So everything here, you're good to go. The plot is on. I go to y equals. I have my 2 equations, and notice my plot is highlighted. So I can go ahead and go over to graph. And as you can see, I have some data points in there. Okay. Now, we can't see everything, so we need to adjust our window. So our window needs to be, if we look back at our data, was from 0 to 70, I believe. So we're going to go to window, and my input, my t values were from 0 to 70, and my y values, my d of t, were really small. So I'm going to go ahead and just say 0 to 10, and then I should be able to see there's my data, there's one of my equations, there's the other one. Okay, let me go ahead and do the same thing in the Casio. I'm going to go back to my menu. I'm going to go back to the stat. Okay, and then we're going to go ahead and graph. So F1. So we're going to go ahead and graph. And we're going to go ahead and graph all right, so I selected F1, graph 1, so there's my data. Nice thing, I didn't have to adjust my window. And to get the regression equation in there as well, I'm going to go ahead and hit calculate. I'm going to calculate that regression, and then I'm going to go ahead and draw it. And there is my regression. Now that's going to be the same as my blue graph over here. The only issue with the Casio, the downfall of this one, is I'm not able, as far as I know, maybe there's a way, and if you find it, let me know. But in the TI, I'm able to graph both equations here along with the data, whereas in the Casio, it looks like I'm only able to graph the data and my regression. But looking at the TI, which of these quadratics fits our data better? And hopefully we can see that the blue one, which is our Y1, that's the one the same as our one over here, fits our data better than the red one that we were given back in problem 2 in the first page. And so the calculator is able to find a better regression using all these data points that we have than just using the 3 points from that previous problem. So we definitely have a better fit with the regression. So let's go ahead and put that in our notes. So it says, how does the model given problem 2 compare to the model from your calculator? The model from our calculator is a better fit. All right, part C. We're now going to go ahead and same data, but now we're going to go ahead and find a cubic regression and maybe see how that compares. So let's go ahead and go back to our calculators and find a cubic regression. So calculators, I'm going to go back into stats. I don't need to enter in my data, it's already entered. I'm going to go over to calculate. This time I want cubic regression, so number 6. This time I'm going to store it again. I'm going to store it into Y3 because I have my Y1, Y2 are all used up. So I'm going to go ahead and put this into Y3 and then calculate. and there is my cubic regression. I'm going to go ahead and do the same thing here. So my data, I'm going to hit calculate, regression, I want cubic, so the y or the x cubed, which is f4, and there is my cubic. Here I also want to copy it, and I'm going to copy it into y3 as well. So that is copied. All right, let's go ahead and write down what our equation was. So our cubic regression, so d of t is equal to, so that is 6.529 t cubed, so that's ax cubed, minus 0.003 t squared, plus 0.187 t, plus 2.703. So there is our cubic regression model. Going back to the calculator, just out of curiosity, I would like to know how this fits. So I go into my y equals, there it is. I have my plot. I have my first regression, the quadratic regression. I have the quadratic that was given to us, and now our cubic regression. So I'm going to go ahead and hit graph. There's my quadratic regression, quadratic that we're given, and then a cubic regression. So the cubic and the quadratic, there's almost no difference between those two. So they're very, very, very similar, very, very close. And just want to see, is there one maybe better than the other? So let's go back to our notes and see what else they asked us to do. So part D, according to research, the average difference in life expectancy between females and males in 1998 was 4.504. Use both the quadratic model and the cubic model we have found in this problem. So this is actually problem 3. So this one, to predict the average difference in life expectancy in 1998. So we're going to do both our quadratic. So I'm actually going to differentiate these. So I'm going to say this is D1, and I'm going to say D sub 2. So D sub 1, D sub 2. We're going to go ahead and use both of those. So we're going to calculate from our first one, 1998. So from 1940, t would be equal to 58. So we're going to go ahead and plug in 58 into our first one, which is under y1. And I put that under y3. And that's going to be our second, our cubic regression model. So this, let's go ahead and label. I'm actually going to write this down here. So this is our quadratic, which I put under y1, and that's going to be d sub 1 of 58, and then our cubic, which I put under y3, not y's, y3, and that's going to be d sub 2 of 58. All right, let's go ahead and go to our calculators and see what it gives us. All right, so I have them stored into both. So I'm going to go ahead and go into my run math in both of these. So I have them under y1 and y3. So I'm going to go ahead and go y1 of 58. That's what we're plugging in. So there's one value, and then y3 of 58. And we can go ahead and compare our values. So very, very, very close. A little bit different, but very close. All right, Casio, just as a reminder, we go vars, and then under graph, y1 of 58, and then y3, y3, let me go ahead and delete all that, delete, okay, y3 of 58. And as you can see, we're getting the same values because we have the same regressions, and we can definitely see that the values are very, very close, but maybe which one is better. Let's go ahead and write down what we got in our notes. So for the quadratic, that was our y1, that was 4.868, and the cubic, that was 4.822. Which model provided a better approximation? Let's look back. What was the actual? Actual was 4.540. And it looks like the cubic gave a slightly better approximation. Not by much, but ever so slight, that's what we want. All right, so the cubic gave a better approximation. Were our approximations overestimates or underestimates? Well, looking at the actual versus our predicted, our predictions were both over the that actual value, so I would definitely say they're both overestimates for sure. All right, and that concludes this lesson. Thank you for watching and have a fantastic day.